Yeah, my name is Jake Lemon. Like I said, I'm based in Michigan, but was formerly based in Pennsylvania and did a fair amount of work in Pennsylvania, West Virginia, and Virginia. But today I'm here to chat with you about some tools we've been using and evaluating to assess groundwater influence as a method of assessing climate resiliency, so that we can better inform our conservation planning with climate efficiency information at finer scales. So the problem is we're the climate refugia, and for the purposes of this talk, I'm talking about thermal refugia. I know there are other flow and drought refugia for consideration, things of that nature, but we're talking just about temperature here. And there's some really nice regional models out there that evaluate the likelihood of cold water fish occurrence under various climate change scenarios. And those can be really useful at sort of broader scales. But once you start to drill down to smaller watersheds, they often break down. And I suspect a reason for this is just that there aren't great broad spatial data sets for groundwater in these areas. And in many areas, groundwater is, a primary source of climate resiliency when it comes to extreme temperatures. So we've been thinking about ways that we can better evaluate groundwater influence and factor that into the work that we do. And we'll talk about a couple of those methods here. One is just simply through the use of paired air and water temperature data. So deploying loggers in the stream and pairing those with air temperature loggers deployed in the riparian area. And I'll talk about a couple of approaches for that here. One of our inspirations for this work was the Snyder et al. Paper in 2015. This was a USGS research project where they were, deployed a network of these paired air, water, and temperature gauges in the Shenandoah National Park and developed some really cool analytical methods for modeling thermal habitat suitability under various climate change scenarios and various groundwater sensitivity scenarios. So how sensitive would groundwater temperature be to air temperature? And just not going to dive into that too in depth here, but just to provide some highlights for our purposes. The graphs here on the left, we have the darker line is your air temperature, the little gray line is your water temperature, and basically you have areas where the two graphs basically correspond with one another, which would indicate less groundwater influence and stream temperatures that are more driven by air temperature. There may be streams where they do correspond, but the effect is dampened, such as in this middle graph here, which would indicate that there's probably some impact from groundwater as well as air temperature driving water temperatures. And then you may have sites like here on the right where water temperature is not significantly, or does not have a huge effect, or air temperature does not have a huge effect on water temperature, which would indicate more of a groundwater influence. And so that's kind of the real basics of what we're looking at here. And as you would suspect, there's a lot of variability in this among watersheds, but there's also a lot of variability within watersheds in regards to groundwater influence. So this is a groundwater index, which I believe is just a numeric expression of the amount of how much groundwater is influencing air temperature. So we have a scale from 0 to 1. Each of these dots is a site in that Snyder study, and each column is a particular stream. And basically what this is showing you is just the level of variability in regards to groundwater influence within streams. So here, Big Run, for example, we have sites with very low groundwater influence and sites with very high groundwater influence. So it just kind of, I think, expresses the need for finer scale networks of these temperature gauges to start to understand and understand the variability within these systems. So based on that paper, we implemented a pilot project using paired air water temperature sensors in partnership with USGS in 2017. And this was focused on 5 focal watersheds in the upper Shenandoah Basin. We actually trained, I think, somewhere around 25 or 30 volunteers to do the logger deployments and retrievals. TU selected the sites, but the data was actually analyzed, and the modeling was done by USGS. We then fed those data products back to us to incorporate into our conservation planning. And just to give a snippet of some of the results that we saw here, this is the Dry River in Virginia, and our observed thermal habitat suitability. So basically, at a very basic level, blue is suitable habitat for brook trout, red is not. We have pretty much suitable habitat for thermal habitat for brook trout throughout the watershed. The triangles are actually sites that ended up going dry. Dry river makes sense. And then we have the most, I guess, dramatic or pessimistic outcome of the model. So this is an air temperature increase of 5 degrees Celsius and an assumption of groundwater sensitivity, that high groundwater sensitivity. And in this case, we are basically showed that we lost thermally suitable habitat in the lower part of the watershed, but sustain it to some degree in the upper part of the watershed. And when comparing these to broader regional data sets, often, in this case particular, regional data sets were much more pessimistic about the likelihood of brook trout persisting in the system. But these data with the better ability to factor in groundwater influence tend to be a little bit more optimistic about these watersheds in regards to their likelihood to sustain brook trout into the future. And so this is obviously really important to TU and other conservation organizations and agencies as we prioritize where we focus our efforts to ensure that we're investing in areas that are likely to persist with good cold water thermal habitat well into the future. And so that was a really cool project that created some nice outcomes for us. Another inspiration for this work was the Hare et al. Paper that was just released last year. And they were basically looking at a couple metrics as a method to assess the influence of groundwater and also the potential depth of those groundwater sources. So at a very basic level, the metrics they're looking at is phase shift. So basically we have a air temperature curve here in gray, water temperature in blue, and the phase shift is just basically measured a delayed response in water temperature to air temperature. So which would indicate that there is probably some groundwater influence, but that groundwater is likely more shallow in that it's affected by air temperature. Here we have amplitude ratio, which is basically a measurement of the difference of amplitude between the two curves, air versus water. Higher amplitude ratio, such as in this curve, would indicate an atmospheric influence. So air temperature is really driving water temperature. A lower amplitude ratio would show sort of the mitigating effects of groundwater in regards to sustaining more colder temperatures in the streams, and likely a greater amplitude or smaller amplitude ratio would indicate maybe more of a deep groundwater influence. And so they actually used some national data sets to start to categorize sites as an atmospheric signature, a shallow groundwater signature, and then a deep groundwater signature. And this was done by plotting this phase shift versus the amplitude ratio, and then setting up some sort of thresholds, which I think are pretty good. Maybe, it's kind of at a point it becomes maybe a little arbitrary to start to set these thresholds because there's probably very little difference from a point on either side of these lines. But generally, it starts to help you categorize these sites as to whether groundwater is deeper, shallower, or whether the site is more atmospherically driven. And, this sort of, again, trying to get at obviously the groundwater influence, but also the resiliency of that groundwater resource to climate change, with the assumption that deeper groundwater will be more resilient to increases in air temperature than shallow groundwater. So that paper inspired us to go out, and we were able to get some funding to do a pilot project applying those methods. The pilot project is focused on watersheds in Michigan, Wisconsin, Idaho, Oregon, and California. And this spring we'll have staff in all of these regions deploying networks of these temperature loggers in some of the focal areas there, and we're collaborating with USGS to kind of dial in, and Daniel Hare as well, to dial in some of our methods and approaches for this pilot project. And so we'll be deploying them this spring, and then hopefully, after we have about a year of data, we'll begin to do some analysis and start to compute some of those metrics. And Danielle Hare has put out has developed an application she calls the Paired Air and Stream Temperature Analysis, or PASTA application. And basically, what this enables you to do is upload your stream and air temperature data, and then compute those metrics, the phase shift and amplitude ratio, automatically using this tool, which is a really awesome tool that we plan to take advantage of. And so we see this as a great way to better evaluate groundwater influence at sort of medium scales in the watersheds, that medium to fine scales in the watersheds we're working in, so that we can better prioritize segments of streams or segments of the watershed where we want to focus our conservation efforts, again, to sustain those well into the future in areas that are likely to be more resilient to climate change from a thermal standpoint. So another approach we're starting to test is the use of thermal imaging to map cold water inputs, and I think of this as just basically a even finer scale approach to get at some somewhat similar information. So this, at a basic level, what we're doing is using a drone-mounted thermal camera, flying sections of rivers, and creating an orthomosaic of the collected images that is used to then identify cold water refugia and cold water inputs, such as seeps and springs and small tributaries. The uses of these data is pretty varied. In some areas we're looking at using it to inform where we focus in-stream habitat work. In some watersheds that are maybe a little bit more fragmented in the thermally suitable habitat, we can focus that in-stream habitat work in segments that are support good thermal habitat year round. Getting a little bit more bang for our buck for those in-stream habitat work. In some areas, they're looking at evaluating how projects may increase groundwater surface water interaction and groundwater discharge into project areas. Sort of another use case that I've read about that's being done in Alaska, and that I'd really like to apply in some of our work areas, is to identify key groundwater discharge areas as a tool for identifying land protection opportunities to preserve those recharge zones for those groundwater inputs and help sustain those groundwater inputs into the future. And so there's lots of applications out there, and every time I talk to somebody about this, I hear of new ones. So I think there's a lot of potential, and we're still kind of in the phase where we're just learning how to do this well. We did some preliminary test flights last summer. I'm going to share just some images from those here in Michigan. This is a river here in Michigan, the Rogue River. The river's flowing from the bottom of the image to the top of the image. We have our visual image here on the left, so we're collecting both visual imagery and thermal imagery. And basically in the thermal image, the sort of yellow and red, that's warmer, the purple is a little cooler, and then the black is the coldest part of the image. And what you're seeing here is a really small tributary. You can kind of see it under the trees here in the bottom left of the thermal image, entering the warmer river and then creating a plume of cold water in that river system. Somewhat similarly, or in that same flight, I should say, we were able to capture some smaller seeps and springs as well. On the left side of the image, you see some very small, sort of darker patches. And what those ended up being when we went out to kind of do some visual inspection with just groundwater seeps, where groundwater was seeping out of a bank of the stream. And so it was a good proof of concept that the images can work. In this case, we were looking for colder groundwater inputs during warmer ambient stream conditions, but we've also looked at and done test flights looking at warmer groundwater contributions during colder ambient stream temperature conditions. And the benefits of that is that it may enable us to do this on smaller streams and maybe do this a little bit more accurately, because you don't have the interference of the canopy quite as much during leaf off conditions. Warmer water will also rise to the surface. We're just measuring surface water temperature here, so it may provide some additional accuracy there. And then there are some other general sort of condition considerations to when this works well that tends to work better in the winter, but I don't have time to necessarily get into all of that. So we're currently working with the U.S. Forest Geospatial Technology and Applications Center to really dial in this approach. We have a collaborative project where we're looking to improve thermal remote sensing mission planning, image acquisition and data processing, and then resource assessment using thermal imagery. And so this partnership started, just a few months ago, actually. And what we've been doing is sort of utilizing their expertise and collectively planning our missions. We went out and did a survey on the ensemble about a month and a half ago of about 2.5 miles of the ensemble, which took us about an hour and a half of flight time. And we're currently in the process of processing that imagery. So GTAC is doing the first round of processing to kind of work through the methods, and then we'll be basically learning from the established methodology that they put together to be able to do this processing in-house moving forward. And actually, I think we'll be getting some of those results tomorrow. So we'll kind of get the results of this first flight, really robust flight that we've done, and in sort of an iterative process inform our mission planning and data acquisition methods for the late summer, when we'll be looking to capture colder groundwater inputs during warmer conditions. And so based on what we learn in our flights and processing and the data acquisition and processing of the data over the coming year, we'll be working with GTAC to develop some knowledge transfer resources to better enable other groups to use staff, agencies, or otherwise to develop this capacity to use thermal imaging and resource assessment. And so we'll be developing some reports for best practices on mission planning and equipment considerations, for image processing, for visualization, and resource assessment. And so it's our hope to kind of develop some resources so that other groups can build this capacity more efficiently within their programs. And so I could talk about this for another hour, but I think I'll go ahead and stop it there and take any questions.
Thank you. Any questions? Dave?
Yeah, hey Jake, it's Dave Thorne. The thermal imaging, can you get absolute temperatures from that, or is it relative, or how much calibration would you have to do for ground truth?
So there is some ability we're using radiometrically calibrated cameras, and you can set sort of ground control points for temperature by basically, deploying temp loggers during flights and get, with some amount of accuracy. I can't say exactly how much you can get absolute temperature. What we've decided is that we're just going to go for relative temperature in our flights. It reduces the amount of time spent on surveying a given reach. You don't have to deploy those calibration points, and just to allow us to more efficiently cover areas in capturing this imagery. So basically, we're looking for relative. We'll find cold spots, and the idea is to follow that up with logger deployments based upon where we identify these cold water inputs, deploying within the identified plumes and capturing ambient stream conditions, and basically characterizing them on the back end has been our approach.
Thanks. It'll be interesting to see too how long those plumes last. Do they mix, or are they like the Amazon and the Rio Negro? They're two different colors for like 2 miles.
Well, I was also wondering, with that plume, a cold plume going into warm water, it should sink. And
That's right.
the fact that he was showing that plume pretty quickly, what's the depth that reads? I assume it's just surface temperature.
Yeah, it's just surface temperature, and basically, I don't have we don't have this stitch into an orthomosaic, but what this plume from this tributary, you saw it sort of billow out about to midstream, and this was about the peak of it at the top of the image. and then it's sort of tapered off as you move downstream. So it is just capturing that surface water temperature.
I just wanted to mention, we found the issue that Dave just mentioned on the Potomac, identifying thermal refuges for muskies in the summer with the same technology. And when you got above where these cold streams were dumping, it was all warm because it sunk right down. And if you walked across the mouth from your waist to your knee, was 90-degree water, but from your knee down, it was 55 or 60. So we weren't able to pick it up, but the river was 3 to 4 feet deep there. So
yeah, actually, it's right out here.
yeah, right, yeah.
We're talking about
It's outside
right
our
out
window.
here. Yeah.
Yeah, and that's part of the reason we've looked at, doing some more winter flights, looking for those warmer groundwater signatures to try to mitigate some of those issues.
Jeff Day, question?
Yeah, thanks. Can you comment on the equipment that you're using? Presumably it's a FLIR drone, is that correct?
Yeah, so we're using a DJI Matrice 200 drone with the DJI XT2 dual visual and thermal camera, which uses a FLIR, I think, Duo Pro thermal camera. So that's what we're using. There's other options out there, and I've done a fair amount of investigation into thermal camera options. That's what we landed on, but there are other options out there.
And the cost?
That cost of the drone was about $6,500, and we're actually renting the camera, and we're able to rent it for about $300 a week.
And have you played around with the consumer grade FLIR cameras that you can plug into an iPhone at all?
I haven't personally done that. It's on my wish list to do a little bit of that. There's some USGS folks here in Michigan who have used some handheld thermal cameras, basically walking. I think they're looking more at wetlands, but we've talked about doing something like that, walking smaller streams. The limitation of this is that it's not really going to work well on small streams just because of the interference from the canopy. So that's another approach that could work.
Yeah, because I've been playing around with the consumer grade FLIRs for years now, and I cannot say past proof of concept that I can really be happy with the results. Of course, I'm waiting for a super hot day, but suffice it to say, I'm very interested in hearing about others experiencing using these $300 or $500 units that you plug into an iPhone.
Yeah, maybe a good follow-up workshop again in the future. There's a lot.
Excellent, thank you.
One more comment from Than, and then we're going to move on.
Hey, Jake, I really appreciate that pilot project you guys are starting up here across the country. So better than anybody else that it's not trivial to organize and train volunteers to do this work. I thought it was a success story from our work in Virginia. That was a good proof of concept. But when you think about going big, do you think this is scalable? Is it feasible to sort of take TU, chapters and to roll it out across the country? Based on your experience, do you think that's a scalable thing to do?
I think the paired air water temperature sensor approach is scalable. The methods for deploying and maintaining and retrieving temp loggers are very simple. I've got a lot of shown success in training volunteers to do it effectively. As you recall, our retrieval success rate for that Upper Shenandoah project was good. We were happy with it. I think increasingly our volunteer base sees the value in better understanding climate resiliency and factoring that into our work. And I think this could really, as we scale this up, it could really pair well with some of the priority waters work that we're doing here, and really honing in on particular watersheds and understanding those watersheds to the fullest, so that we can do good conservation planning there. And so it's a good volunteer opportunity in that it's relatively simple. It creates really compelling data, and it's not a huge, intense time investment as well. Really, you're talking about going out and deploying a logger, and then either downloading it at some interval or retrieving it. So I think it's got a lot of potential there.
Well, thank you, Jake. Yeah, let's continue the discussion.